Okay, so I want to give you guys your first existence and uniqueness theorem. Oh, happy day, you say. This will allow you to know that both there are solutions to a differential equation of a certain form, and those solutions are sometimes unique. It will not, however, allow you to find them in any better way. Does that make sense? Like, this is a theorem that says this thing exists and it's unique under certain conditions. It is not a theorem that says, and you can find it. Does that make sense? Do you guys remember an analogy for this? What's another theorem like this?
I don't know. Is it the intermediate value?
Yeah, the intermediate value theorem is this same thing, right? It tells you that there is a spot where something interesting happens. It does not tell you how the heck you should find that spot. Cool? So these are a very similar thing, and they're a little bit frustrating for students because of that. So here's I'm going to call this take one. We're going to have a whole bunch of existence and uniqueness theorems, and they just kind of nest. They're like a little Russian nesting doll. It gets better and better as we go on. So if we have f that's continuous on a rectangle made out of AB crossed with CE, I'm going to write some stuff down. If you have questions about what exactly I mean, we'll talk about it in a second. And there's a point, x naught, y naught, that's in that rectangle. Then the IVP, y prime is f of x and y, with y at x naught is y naught, has at least one solution on an open subinterval of a B. Whoops. And obviously, that part needs to contain x naught. Otherwise, this would be bizarre.
What does it say if you're on the bottom line, or second bottom line?
Okay. On an open subinterval of AB containing x naught. In other words, there is a rectangle that's AB by CD, right? You guys were all on board with multiplying intervals together? Okay. So I've got a rectangle R, that's this. My function f is continuous in there. And I'm only doing the very specific form of a differential equation that's y prime is f of x and y. So please note this f is not the f from non-homogeneous differential equations necessarily. Could be if you rearrange things appropriately under really specific conditions. Like specifically if the coefficient p on y is 0. Right? So if you have y prime equals f of x, that would be one of these. Also, please note this is a function of two variables, x and y, right? You guys with me on that? So this is a like Calc 3 style function, not like a Calc 1 style function. So that thing being continuous is a little bit weirder. Remember, limits in 3 dimensions are a little funky sometimes. Okay. So I have also y of x naught is y naught. What's that business?
Initial condition.
Yeah, that's just some initial condition, right? And presumably x naught is in here.
Is that just?
Probably we should ensure that. Right, because it definitely wouldn't work if I didn't know that this thing was continuous at least near my point.
Why not should be between C and D, right?
Thank you. Thank you. Okay, so we have a very specific form of a differential equation with a specific initial condition, and we say, okay, so under those conditions, and so if we have a rectangle where the function's continuous and an initial condition that's inside the rectangle, then we have at least a solution on some subinterval containing x naught. You guys cool with that? Is this a huge surprise? Somehow not really, right? Like, y prime equals continuous thing, probably I could solve that. Like, we've been solving a bunch of those. This at least one solution is a little funky, right?
Yeah.
Because that's the existence part. This is saying there could certainly be lots of solutions. You guys see that? Like, for instance, I could have this as a solution and also that's a solution. Right? Those might both go through this same point and satisfy this differential equation.
So this is one of the things I was wondering. If we, here now, we have like an XY plane basically, we're drawing graphs on there.
Yep.
But this also is representing f of x and y, so we should have heights coming out of the board, right?
Oh yeah, is it R2 or R3?
Oh, this guy?
Yeah. So
Yeah, but this f of x and y, right, the heights coming out of the board, they aren't recorded as heights, they're recorded as derivative information. Right, so this is telling you the derivative is related to x and y. Right, so the slope is a function of the point you're at. Does that make better sense? So there's not heights, this is strictly two-dimensional.
Okay.
So instead of being recorded as heights, they're recorded as the slope of whatever curve they're drawing,
So we
right?
plug in an x and y on that thing behind you, and then
And then we'll get a derivative.
it'll give us a slope
Yeah,
of whatever line is there.
yeah.
And
It'll
is
give us
there-
the slope of the solution at that
Is
point.
there only one, or can there be more than one slope?
Because f is required to be a function, there's going to be one unique slope
Okay. But
for
there's
every
only, like-
given point.
Okay.
I'm a little confused on how there's only one unique slope when you just said like you could have two different slopes in the same unique spot.
So what I'm saying is that these two satisfy, and this is a little bit weird, right? So what I'm saying is that right here at that initial condition point, right,
Yeah, x not y not.
there's a slope that's given, right, by this. There's also a bunch of slopes that are given in a bunch of other places. Right? So like here, the slope is this. Up here, the slope is this. Down here, back here, the slope is this. Over here, it's this. Right? And what I have is two curves that have the same derivative information here at that initial condition point. Otherwise, they're totally separate, and so they go through separate points, so they have separate derivative information. This is not a particularly likely case, but it is possible.
So, under this, if they intersect, they will have to have the same derivative.
Yeah, and that's because I'm solving a differential equation.
So you're never going to have one go like that, one go like straight
Yeah, they
down.
can't transversely intersect. They have to kind of kiss and diverge. You guys all on board with that? That said, the uniqueness part of this kind of implies that this is not very likely. Because the uniqueness portion of this, you guys know that these guys mean unique?
What else?
No? Okay, so mathematicians use BAMs, exclamation points, to describe when something's unique. Okay, so if I wanted to do a good job giving you mathematical symbols, I would say this is the existence portion, right? And this is a symbol there exists, backwards E. And over here, that thing is unique. So if I'm writing an existence and uniqueness theorem, I'll oftentimes write this. There exists uniquely. You guys all good with that? A little funny notation for you.
Isn't that a television show?
And then what? I think in E, the E is
not that
regular.
Yeah.
Anyway, point is. So if as above over there, how about over there? So if is over there, and Fy is continuous. Then the solution to y prime is f of x and y with y of x naught is y naught is unique on some subinterval containing x. In other words, it exists if your function f is continuous and some other assumptions are reasonable. And it's unique if the fy is continuous. What's an fy?
Is that the y partial?
Yeah, that's the y partial of your function f. You guys see that? So if the function's continuous, cool, you have a solution. If that function's y derivative is also continuous, then you know that function, that solution, to be unique.
That was my main question, is what the heck is f sub y here? Like, what's
Yeah, it's
the
partial.
y? What's the y partial? What's it look like on there? Or I was thinking there's a relationship between the.
Yeah, so the y partial, right, is the rate of change of f with respect to y. You guys all see that? What is f describing? Well, f's describing the slopes, right? You guys see that? Are you with me? So what this is saying is the rate at which the slopes change is continuous with respect to changes in y. In other words,
Oh yeah.
if you go this way a little bit, the slopes change continuously. You guys all on board? That's kind of cool. That's enough, apparently, to ensure that I can't have branches. You guys kind of see why? I think it's sort of intuitive, right? Like, if you had a branch, right, that would be two spots where the derivative information was kind of, one was going up and the other one was going down, right?
For the same x.
It's likely to be two y partials.
Yeah, that's weird, right? Like, that doesn't seem like it's going to happen unless there's a spot where the slope's 0 in the middle, and if there's a spot where the slope's 0, then why are you changing up or down?
Yeah, then wouldn't that mean you have two different y values for your 1x? If you have branches too?
It would mean you have two different possible functions, y of x, right? Yeah, in other words, your kind of long-term behavior is not uniquely determined, which would be a little weird in differential equations land, because I like to think about these as like flows of stuff, right? Like flows of oil slicks on water or something. So if I have a flow that has this kind of a branching behavior, that would be like, well, it might behave all kind of predictably for a while, and then it could follow either one or the other of these like divergent paths. Like, it could end up in two drastically different areas. That seems like really weird without having gone through that kind of intervening space. Like, that's really strange. You guys see that? Like, normally this is a position and a time variable, right? That would be really bizarre. But it's not disallowed by this. It's just,
How did you word what FY represented?
so Fy is the change in F per change in Y. But F itself is the derivative information. So it's the change in the slopes per change in vertical movement.
So changing F as Y changes, that would almost be like an acceleration then, like practically.
In the Y.
Yeah, you could think of it that way, right? Because this is the slope, right? So you're changing the slope, the kind of velocity per change in, yeah. Yeah, that's kind of reasonable. It's a little bit weird because it's not, this thing is a dy dx, right?
Yeah.
And so if I'm taking a partial of dy dx with respect to y,
That's not exactly.
Yeah,
like
it's not-
acceleration, 'cause that would be like taking, you know, the partial with respect to distance, change in distance rather than change in time. If you took that partial with respect to x, that would be like acceleration.
yeah, two x derivatives, right, would be acceleration.
Yeah.
This is an x derivative and a y derivative. This is those mixed partials, right, that are kind of weird anyway. But yeah, that's what's going on. We're getting the change in slope per vertical change. And we're saying as long as that function's continuous, you get a unique output, right? Your solving of your differential equation gives you a unique answer. You guys cool with this? You want some examples? Yeah, desperately.